All right. In this integral, sorry, in this video, we are going to start introducing integral theorems for evaluating complex valued integrals. So the first theorem we are going to look at is called the independence of path theorem. And we've sort of alluded to it in the previous video when we worked through those examples, and one of the examples had exactly the same value irrespective of the path along which we integrated. So this theorem says if f, small f and big F are continuous and analytic in some domain R, so in some region R, and the derivative of big F is small f, which means the integral of small f is big F, then for any piecewise continuous curve in R joining Z1 and Z2, then the integral of small f from Z1 to Z2 is going to be equal to big F evaluated between Z1 and Z2, which is equal to big F at Z2 minus big F at Z1. So what this theorem is saying is that this integral just depends on the starting and the end point of the contour C. So if this is our contour C, this is Z2, this is Z1, then it is saying the value of this, if F is analytic in this whole region here, so let's imagine so if F is analytic in the whole region wherein the curve is defined, then the value of the integral is just going to be dependent on the two extreme points of the curve. What this means, because it says independence of path, of course, if we define another path, suppose this was C1, if we define another path, but it also begins at Z1 and finishes off at Z2, then the value of the integral is still going to be exactly the same thing. Now, so two things to note here. The first one is that this theorem is an extension of the fundamental theorem of calculus that we saw in in our first year course on integration. And the other thing is that it suggests that if we integrate this function along this one and then come back along this, then we should get 0, because the integral from Z1 to Z2 is going to be the negative of the integral from Z2 to Z1. And this is exactly what the next theorem is all about, which is Cauchy's integral theorem. It is also called Cauchy-Goursat, because Goursat was involved in part of the proving of the theorem. So this one says if F is analytic in a simply connected region, we are going to explain what this means in a moment. So our region R is simply connected for any simple closed contour C in R, then the integral around C of F is always going to be 0. So let's talk about what a simple closed contour is, and then we're going to talk about a simple connected region. Simple closed contour is a closed contour which is such that it does not intersect itself. So this is an example of a simple closed contour. Now, so contours have a sense of direction. So if while traversing on the contour, the inside or the region enclosed by the contour is on your left, then the direction along which we are traversing this contour is called positive. So typically your positive direction is going to be your counterclockwise. Then so if this is the definition of a simple closed contour, so the contour should be closed and it should not intersect itself. So a region covered by a contour which is in the shape of like infinity, this one is not going to be simple closed because it intersects itself once. In fact, this one is called let me talk about the region. So a region is called simply connected if it's enclosed by a simple closed contour. Okay, this region here, which is enclosed by the figure infinity or 8, that one is called doubly connected because this contour intersect itself. Cauchy-Goursat or Cauchy's integral theorem is all concerned about the case where the region we're talking about is simply connected, and it says the integral around a simple closed contour is always going to be 0 if f is analytic. We note that the condition that f of z must be analytic is necessary rather than sufficient to have this. What this means is that if f of z, so it means this is a one-way implication statement. If f of z is analytic in the region, then this integral is going to be 0. But the other way around is not necessarily true. So it is possible to get integrals whereby the integral around a simple closed contour is 0, and yet the function is not analytic. Okay, so and we're going to see an example on this. Now, the other thing, technical thing that we need to note is that when we say inside a closed contour, we mean all the points inside, but also points along the boundary are also considered to be inside the region. So the boundary of the region or the actual contour is actually part of the region enclosed. So we consider those ones to be inside. All right, so with those two theorems, we're just going to look at a few examples. Example number 1, we want to evaluate this integral here from minus pi ion 6 to pi ion 6 along a contour. So let's see how that one works out. So just alright, so we want to evaluate the integral of 2 minus e to the minus 2z dz from minus pi ion 6 to pi ion 6 along any contour. Just as a tip, if the question says along any contour, typically it means that the function we're dealing with is entire. It's got no singular points anywhere. So here 2 is not singular anywhere. E is also not singular anywhere. If you remember, sine, cosine, hyperbolic sine, and hyperbolic cosine are the others, or in polynomials that are not singular anywhere. Well, of course 2 here. is a polynomial. So it's always useful to make a sketch. So here we are integrating from minus pi I over 6 to pi I over 6. However, since this function is analytic everywhere, we do not have to define the function or the equation of the contour. So let's just show you how this works out. So we just evaluate this integral like our real integrals, 2 minus e to the minus 2z dz. So we're just going to say, well, integral of 2 with respect to z is going to be 2z, and integral of this one is going to be plus 1/2 e to the minus 2z. If you have to revise these from our first year calculus course, by all means do that. We are going to need to be okay with evaluating integrals of all these elementary functions. Right, then now we plug in the limits. So for the first term, it's going to be 2 into pi I over 6. It's going to be pi I over 6 because it's minus negative pi I over 6. And then for the second term, is going to be 1/2 of e to the negative 2 pi I over 6 minus e to the negative 2 minus pi I over 6. This one is just going to work out to 2 pi I over 3. The second one is going to be 1/2 into e to the minus pi I over 3. Okay, this is going to be minus e to the positive pi I over 3. Now you're going to notice that this looks very much like the sine type of group of terms, but this one should be positive. So if we put a minus here, that should sort that out. So then we're going to have e to the pi I over 3 minus e to the minus pi I over 3. And in fact, we can now take these two into the denominator. Then it's now almost like sine of pi on 3, except that we need an I in the denominator. So we're going to plug in an I in the denominator. So if you plug in an I here, and then we must multiply it by I there. So this is now 2 pi I over 3 minus I sine pi over 3. Sine pi over 3 is just root 3 on 2. So it's going to be 2 pi I over 3 minus I root 3 over 2. So that's going to be the value of that integral there. So yes, we can do one more example. In number 2, we have evaluate the integral. So let's start with 2a. Evaluate the integral of z dz over z squared minus 2 from 1 to negative 1 minus I along any contour that does not pass through plus or minus root 2. Okay, so again, maybe let's just cut and paste that. Right, so in this question we are looking for the integral of z over z squared minus 2. And then they're saying along any contour that does not pass through plus or minus 2. Now notice that plus or minus 2 are the 2 points where the denominator is 0. So those are the singularities of the integrand. So they're saying we want to and evaluate this along any path that is not going to include the singular point. So everywhere else this function is going to be analytic. So that means we can apply the fact that the integral is just going to be a function. The value of the integral is just going to be a function of the starting point and the end point of the integration. So if this is root 2 and this is minus root 2, we want to evaluate the integral along any path that does not include those two. So we're integrating from 1. So if that is root 2, 1 is going to be somewhere there, and then we're integrating to minus 1 minus I. Minus 1 minus I is going to be there, minus 1 minus I. So any contour that does not go through these two is going to be fine. Then we know that the value of the integral is going to be a function of these 2 points here. Now notice that like in the first case, if the function is analytic along the path of integration, we can just evaluate this exactly using the methods from the first course in calculus. So that's exactly what we're going to do. So we've got the integral from 1 to minus 1 minus I z dz all over z squared minus 2. There's at least 2 methods we could use to integrate this. The shortest one is going to be the u substitution. So that's exactly what we want to do. So if we let u be equal to z squared minus 2, then du is going to be 2z dz. So z dz is going to be half du. Then when z is equal to 1, u is going to be negative 1. Then when z is negative 1 minus I, u is going to be 2i minus 2. Just make sure you can go through these, you can confirm through these if we are going a bit fast for you. So that's going to be that. So I is now going to be the integral from minus 1 to 2i minus 2. We're going to have half du divided by u. This is going to work out to half ln u. We are integrating from minus 1 to 2i minus 2. So this is going to be half ln 2i minus 2 minus ln negative 1. Now we know that ln is a multivalued function, so the one thing that is worth noting here is that when we work out the values of integrals, typically we work with the principal values of these functions if they're multivalued. So like ln 2i minus 2, the magnitude or modulus of 2i minus 2 is root 2. The argument is 3 pi over 4. Take away, for negative 1, the magnitude is 1 and the argument is pi. That's the principal value of the argument. So when we combine these, ln 1 is 0, so this one is going to disappear. So it's going to be ln 2 root 2 plus, I think it's going to be 7I pi over 4. Or maybe not, because I'm subtracting, so it's going to be negative pi on 4, because it's 3 on 4 minus 1. So this is going to be negative there. So that's going to be the value of that integral there. Okay, now we're going to give you an opportunity to have a go at number 3 and number 4 before you have a look at our solutions. So just pause the video. There is number 3 and there is number 4. There are questions of a similar nature to what we did. So in our number 1, evaluated something along any contour, so that is a similar question in number 3, and then number 4 along any contour that does not pass through 2. So please just have a go at those two and then pause the video. Then when you continue the video, then you can compare with our answers, just to make sure that you are getting these ideas. All right, we're going to scroll down to our solutions for number 3 and number 4. We just realized that we also by error skipped number 2b. So if you'd like to have more exercise, you can have a go at b. Pause the video again before you look at our solution, which we're going to present after number 4. All right, so let's scroll down to see what solution for number 3 looks like. Hopefully it tallies with your work. Okay, so here we've got the integral of 2z e to the minus z over I dz from 0 to pound 2. Again, the question says along any contour. We said that usually signals the fact that the function involved is analytic everywhere. So here we are integrating from 0 to pi on 2. Z is a polynomial, 2z. E is analytic everywhere, well, so long as this z is not in the denominator in that exponential. So long as we don't have anything like e to the z. If you've got e to the z, then when z is 0, this thing is not analytic. But so long as z is in the numerator, well, besides, if you've got e over z, then 1 over z is not a polynomial anymore. So the first thing we're going to note here is that e to the minus z over I, in fact minus z over I is the same as, well, minus 1 over I z minus, well, 1 over I is minus I. So this is just the same as e to the z. So that thing is the same as e to the iz, I mean. And then this type of integral we can evaluate using integration by parts, or quicker by using tabular integration. So if we take the 2z and differentiate repeatedly, and then we take this one and integrate, so we're going to have to divide by the derivative of iz, and then the first pair is plus, the second pair is minus. 1 over I is negative I, so that's going to be negative 2iz, and then this is minus and minus, that's going to be positive. And then if I plug in pi over 2 here and here, and then plug in 0, this term is going to disappear. We're just going to have this one, e to the 0. Then this works out to 2 minus pi I The 2's cancel out. E to the pi I over 2 is I minus 2, and then remove brackets. It works out to that. This function is analytic everywhere except at z equals to 2. So it only has got a problem. It's singular there. But we're integrating from 0 to 1, and then that's why the question says along a path that does not pass through 2. So that means everywhere here this function is analytic, so we can integrate as if it was a real function. So to do that, we need to first divide here, because this is an improper rational function. So if we do divide, you can divide like this. Of course, you can use synthetic division as well. We find that the quotient is 2 and the remainder is 4. That means we can write this function as 2 plus 4 over z minus 2. Then integral of 2 is 2z. Integral of this is 4 ln z over 2. If we plug in 1, we get this. If we plug in 0, this disappears. We get that. Then, as we already mentioned, we just do the principal values for the ln. So it's going to be 2 into 2 plus 4 into ln 1 plus pi I. It's going to be ln 2 plus pi I again. And then when you remove brackets, this is what we get. It's going to be 2 plus ln 1 is 0, 4 pi I, minus 4 ln 2 minus 4 pi I. So the pi i's are going to cancel out, and so this is what we're going to get. For the part B of number 2, we have got this function here, which we said is singular at plus or minus root 2. But we're integrating this around the circle mod z is equals to 1. Now you can see that along this circle and inside the circle, the function is analytic because it's only singular here. And so by Cauchy's integral theorem, the value of this integral is going to be 0. So we just say I is equals to 0 because this is analytic everywhere, or we can say I equals to 0 by Cauchy's integral theorem. Right.